Let's go back and review some concepts around categorical variables. We've got two categorical variables in our data set. We have gender and hair color. And so we could ask, does hair color relate to gender of the Academy Award winners? Another way of saying that would be, is there a difference in the number of men and women with dark hair who win or with light hair who win? So we've got our two variables, gender, categorical, groups, labels, words, with two levels. Hair color, also groups, labels, words. And this one's got three levels, light, dark, and red. Let's start by just counting how many people fall into female with dark hair, female with light hair, male with dark hair, male with light hair, male with red hair. And so we're going to calculate a frequency table, just like we did a few weeks ago. So we're going to create a 2x3 contingency table where we're going to just count how many people fall into each of those groups. So let's see, I'm going to go ahead and just start it here. I'm going to put my levels of the hair color across the top. So light hair, dark hair, red hair. Then I'm going to put my labels for the gender down the side, male, female. And what I want in each of these cells is a count of how many people fall into the have is male and have light hair. We're going to do a conditional count, a count ifs. That was a plural, count ifs. If you need to review those, the logic on those, go back to tutorial 3 that we did those. In this cell, we're going to insert a function. We're going to search for count. We found count ifs. Insert. We want if column C for the criteria range is male and click. Column G for the hair color criteria light. So go ahead and fill in the count ifs for the rest of that table. You can watch me do it. I'm going to fill across. I know it's not going to be perfect. And then to edit K3 here, I'm going to double click. And I see how my blue and red columns are highlighted. If I come and hover right on the side edge, it turns into a hand. I can move that back over there. So if C is male and G is, what do we want this one to be? Dark. If C is male and G is red. I'm going to use fill to fill down. It should work a lot better because at least the column references will be right. And then I just need to come in and edit each of the criteria to be female. Is that what you calculated? Let's add our totals columns. I'm just using equals sum, open paren, and clicking and dragging. That's good to see that we've got 88 males and 88 females. That sounds right. And that's good to see that the number of the hair colors add up to 176. That sounds right. It's always good to just check that your data has still got integrity. So we have the raw numbers. Do you remember what we do next? We need to calculate proportions or percentages. Even though we've got the same base rate of males and females, and so the 34 can be directly compared to the 26, it's just easier for us to do the work so our audience doesn't have to and standardize and put everything onto out of 100 or percentages. So are we going to calculate our proportions of the males? What percentage had light hair? What percentage had dark hair? What percentage had red hair? Or are we going to calculate our proportions of the people with light hair? What proportion were male and what proportion were female? Those are both equally accurate ways to manage this data or to organize this data. It's somewhat up to you. If one variable was clearly the predictor variable and one variable was clearly the outcome variable, then we would certainly group it by the predictor variable. In this case, they're not really in that sort of relationship. So the next question is one more of an enduring characteristic? I think I would go with, of the males, what percentage had light hair and dark hair? Of the females, what percentage had different colored hair? But it is somewhat up to you. Let's make another contingency table. I'm just going to copy the group labels. So if I want to say, how many of the males had light hair, that would be equals those that had light hair divided by the total number of males. And I can fill that across. So let me fix those. Well, I can highlight all of those and fill them down. I want to put those all into percentages. I want to increase my decimal places. How might we best visualize this? Do you remember? When we're dealing with two categorical variables and we've got frequency counts, we need to have frequency up on the y-axis and one of the variables along the x-axis and another variable over in the legend. We're talking about a clustered column. Let me highlight all the data with the labels. And on my insert ribbon, choose that clustered column. We've got two variables, neither of which is really a strong predictor of the other. Again, male and female is the more enduring characteristic. So you need to ask yourself, how do you want to see this? Use the switch row column. Given that we summarize these percentages by gender, it makes more sense to have the groups along the x-axis be gender and the legend be the hair color. I'm just thinking, this is parts to a whole. What's the other option for the chart if we've got parts to the whole? I've highlighted my data. Let's come up and choose that 100% stacked column. Now this is not right. We don't, because these numbers are organized by gender, so we definitely need to switch the row column. And so that might be a more accurate way, another way of displaying this same data. You're going to want to adjust the color palette and add the chart title. Let me do some of the formatting here. I would like to move the legend to the right-hand side. I would like to have frequency as my y variable, y-axis. Gender. Do you remember the formula for the chart titles? It would be outcome variable by predictor variable. We've got the hair color listed as the more outcome variable. So hair color by gender. We don't want to use that blue and that orange. That's very distracting. Let's choose a monochromatic. The outcome variable, well, the second variable here is hair color, so we could do something kind of more cutesy. If I click on the particular column of the data, I can come over here to that format data point and select a specific color. So what's this? This first one is light hair. So we could make that blonde. Make sure you do that for both. And for dark hair, let's make that brown. Did you see what I did differently there? So Excel will allow me to individually select the parts of the graph. But then if I select them both, or if I select them over here in the legend, it's going to apply to everything, and that might make that easier. Oof, that's pretty ugly too. Well, you keep working on it. When you have formatting that looks good, then we can start thinking about interpreting that. Just like with the comparing groups, we need to have a way of making a decision. We can look at that pattern and feel pretty confident just with our visual reasoning skills that those are different patterns. I mean, for one thing, if I said someone just won the Academy Awards, they have red hair, you would feel pretty confident in predicting what gender they were based on the previous winners. So we can look at the pattern, but we need an objective way of deciding. We need another inferential statistic. Again, I'm going to introduce this idea of the inferential statistic, but we're not going to get into calculating it or any of the specifics. That's for your statistics class. This inferential statistic we're going to talk about now is one that allows us to make this sort of frequency comparison. And it's called chi-square, and it's the Greek letter chi squared with the exponent 2. So it allows us to objectively decide if these frequencies follow the same pattern. So let's say it looks at if there are 60 people with light hair and half the people are male and half the people are female, well, we'd think that half the people with light hair were male, and we see that's not quite the pattern there. More decisively, if we look at these 100 people with dark hair and say, if it was the same pattern, it should be 50-50. And actually 50-50, right? And that's really quite different from 50-50. And then with this, if there's overall 16 people with red hair and we've got an even number of men and women, what would we expect? How many males and how many females would we expect to have red hair? Right, 8 in each group. So this inferential statistic chi-square calculates those numbers of what would we expect if the patterns were the same, and then calculates the difference. What's the difference? And it uses subtraction to calculate how far off the expected pattern is the actual observed pattern. And so it's going to give us an objective way of saying, are those different? Are they due to a real difference in the pattern? Or is it just chance. Like the t-test that we just talked about, if the patterns are actually the same, your calculated inferential statistic is going to be really close to 0. Also, just like the t-test, we're willing to decide that the patterns are different if the probability of calculating that chi-square is less than 5%. And so you'll see that written as p is less than 0.05. It's that same idea that if they were the same, then we would calculate this big of an inferential statistic maybe 5 out of 100 times. I've gone ahead and calculated that chi-square for you, and it is statistically significant. The probability is less than 0.05. So please go ahead and copy that graph that you've chosen and that you've formatted into your write-up and include an interpretation. Where is the difference in the patterns? Be sure that you interpret the data, not just type it out.